From the beautiful South Studios of Way Happy, this is Mr. Meyer and 1-3 limits and their properties. All right, so we've done some graphing of limits and we were able to look at the limit when we see a graph. And now we are going to maybe go a step further and try to do it a little more analytically or algebraically, whichever one you want to call it. So there was our objectives as you saw, and let's get started. So a lot of functions, you can evaluate the limit by what we call direct substitution. And direct substitution, not a bad thing. It's actually something kind of nice, and it makes our life a little easy. What that means is if you're going to evaluate the limit as x approaches c of a function, you might be able to just plug that value c into the function and get the limit. That means that the function was continuous at whatever number you were going at. And we're going to talk about continuity a little bit later. We've already done it before in other classes, but we're going to talk about it again later in a couple of sections. And so here are some theorems, and it looks overwhelming. Here's some theorems that they have that talk about continuous functions and what you can do if they are continuous, what you can do with their limits. And it's meant to make them easier, right? And these properties are super cool, but they're really straightforward. So you can look at them, and I want you to think about them, maybe come back to them later on. But they're definitely something that may or may not scare you at first, but will make your life a little easier. So let's go on to example 1, and I'll show you what I mean. So here we describe the limit of function f evaluated at c is going to be a 4. And the limit of g is going to be a 2. All right, now according to all of this, if you look at A, then I'm asking you, what's the limit when we evaluate the function as we approach some number c, which we don't know, of 5g to the x? Well, that's right here. That's called the scalar multiple, right? And the scalar multiple just says, hey, you take that scalar, the number that's being multiplied, and you multiply it by the limit of the function, and you get the same answer. So this would just turn into 5 times, what did I say g of x was? 2? So you would get 10. So the limit of 5g of x is just 10. That's what I mean. Kind of feels like something that you would have done naturally. It'd be like, hey, I have the limit of g of x and the limit of 5. Guess what? I'm just going to make it the limit of 5 times g of x, which is 2. Now, what about b? I have this always reminds me of when I was in school. They would say the limit of the sum is equal to the sum of the limits. That's right here, right? The limit of the sum is equal to the sum of the limits. So if you have the limit of two functions that are added together, then you could just take their limits and add them together. So this would just be 4 plus 2, which is 6. And you'd be like, oh, the limit of the sum is 6, right? And then how about C? The limit of the product is equal to the product of the limits. And so again, feeling very comfortable in doing this, all of a sudden I would be like, hey, this is just 4 times 2 or 8. So the limit would be 8. And how about the quotient? The limit of the quotient is equal to the quotient of the limits. Not a big deal. F we said was 4, G we said was 2. So the limit is 2. And that's limits. If you actually, somebody tells you the limits and then they ask you to do a sum or a difference or a quotient or a product or a scalar, it doesn't matter. And probably what I should have mentioned way back in the beginning too was, these guys are kind of important too, but they're kind of obvious that these limits that you take them of just of some number and you're approaching, x is approaching c. Notice there's no x in the problem. So the limit is just going to be that number. And that's why this 5 was just 5. All right. Now that seems a little obscure probably to most. And what I want you to look of is this next group of 2. It says, or looking even to the right, direct substitution just says, hey, look, when you have a constant value, you're talking about a continuous group, all those rules up top could be just done by what we call direct substitution. So direct substitution means it's a nice, pretty graph. There's no jumps. There's no asymptotes. Well, where you're evaluating the limit, there's no jumps and there's no asymptotes and there's no holes. There's nothing funky going on. It's just a nice, smooth graph. And so you could just plug it in and that would tell you the limit, right? And so if you look at example 2a here, if I plug a 1 in, I would just get -1 squared plus 1, or -1, because 1 squared is 1, and then make it negative, so it's -1, plus 1, 0. Guess what? The limit is 0, right? Nothing wrong with that. Limit is 0. All right, what about here? If you plug a 3 in to b, if I go to b and I want to plug a 3 in, I would have the square root of 3 plus 1 over 3 minus 1, which is the square root of 4 over 2, which is 2 over 2, which is 1. So the limit of that is 1. If you looked at the graph, you would see the y values are 1 when the x value is approaching 3 from either side. Not a big deal. This is probably the most simplest thing you could ever have when you talk about limits, and it's probably the one thing you'll forget by the end of the chapter. All right, look at this on C. I'm going to plug in 0 for H. Ooh, I changed variables on you, H. So go to all the H's and plug in a 0, and you would get 3 times 0 squared plus 2 times 0. Hey, that's going to be 0 plus 0, which is 0. So another limit that was 0. Crazy. Or even look at D, plugging in the limit of this was H goes to 0. Well, this didn't have any H's in it. This is going to be 0, and this is going to be 0, right? So I'm going to have the limit really of 3x squared. And remember that property up there that's, as H goes to 0. And if there's no H's in the problem, then the limit is just the thing in the parentheses. So this is 3x squared. So be careful with your variables as you do these limits. So again, direct substitution, probably the nicest thing in the world. If you can play, if it's a nice continuous function, or at least continuous at the point that you're evaluating it at, then enjoy. Plug it in and let it work and be happy. All right, let me ask you a question, and I'll be right back. All right, nice work. Now let's talk about some strategies, because you just did a bunch of direct substitution. That was fun. It was easy. We're not worried, right? Now, what about if the limit can't be found during direct substitution? And then don't forget, there's those 3 times earlier in a video that sometimes we just don't have a limit. It doesn't exist. So keep that in the back of your mind. But other times there will be where you do direct substitution, and what happens when you do direct substitution, what the heck? What happens when you do direct substitution is that suddenly the limit gives you a result of 0 over 0. No, right? You can't do that. That's called indeterminate. 0 over 0, I can't determine what that is. There's some reasons for why it's called indeterminate, right? Because 0 over anything, the answer is always 0. Oh, wait. But if it's 0 over 0, the answer should be 1. So because 7 over 7 is 1 and 10 over 10 is 1. So wait, one person could argue the answer should be 1. One person could argue, no, the answer should be 0, and they'd both be right. So all of a sudden, I can't determine what 0 over 0 is. It's just, I can't define it. It's undefined. So known as the indeterminate form. And what does that mean? That means do something else. If you get 0 over 0, something bad has happened and you need to do something else. Now, what are those things you could do? Well, the things you could do are pretty straightforward and pretty algebraic, right? We can't have denominator of 0. That's just bad in limits. So you might have to try to cancel like factors. All right. You might have to rationalize the numerator. What? What algebra 2 is rationalize the denominator? Guess what? Rationalize the numerator now. Or maybe we need to simplify some algebraic mess and see if direct substitution works then. So there's some more examples of complete madness. So here's example 3. Example 3 says, all right, I want you to find the limit as -1. So look, as you plug in -1, you get 2 plus 2 minus 3 over -1, right? I'm sorry, 2 plus 1 minus 3. So you get 0 over 0 when you do direct substitution. Oh, no, here, direct substitution would yield 0 over 0. That's not good, right? So it doesn't help. So now what is the heck's the limit? And say you don't have a graphing calculator, you don't know what the graph looks like or whatever. Is there an algebraic way? Well, yes, there is. One of the ways is to try to factor, maybe try to reduce something. So let's see, can this thing actually reduce? Well, if I factor the top, and you remember the way I like to factor, I multiply the outsides, A and C. So 2 times -3 is -6, and they got to add up to the middle, -1. And what two things multiply to -3 that add up to -1? That would be -3 and 2, right? They multiply to -6, they add up to -1. And then remember my bizarre bottoms-up technique says you have to divide by whatever was out in front. So you get this. Divide them both by 2. What does that mean? that means that one factor was x minus 3 over 2, and the other factor was x plus 2 over 2. And I clean those up. So this one becomes 2x minus 3, and this one becomes x plus 1. So all I did was factor the top. So our new problem becomes the limit as x approaches negative 1 of the top, which is 2x minus 3 over x plus 1, all over the bottom, which is x plus 1. Oh, look at that. This factor cancels this factor. That would make a hole in the graph, but we don't care about the graph. We're talking about the limit. So we're saying the limit as x goes to negative 1 of what? 2x minus 3? Hey, I bet that's continuous at negative 1. I can plug negative 1 and tell you the limit. The limit would be, let's see, plug in a negative 1, you'd get negative 2 minus negative 5. There's your limit. So a few seconds ago, we couldn't do it because it was 0 over 0. But now all of a sudden, with a little bit of reducing, a little bit of algebra, I can tell you the limit is negative 5. And I'm feeling pretty good. What about the next one? All right, and now example 4. So let's look at example 4. The limit as x approaches 3 of that crazy function. You plug in a 3, notice what's happening. You're going to get 2 minus 2 on the top, which is 0. You're going to get 3 minus 3 on the bottom, which is 0. You got 0 over 0. Dang it, right? Direct substitution didn't work. All right, let's go on to another technique. Now I see a square root. Square roots are kind of gross when they're in the numerator. That means that, if you plug it in, the top is 0. So let's rationalize it. So how do you rationalize it? You multiply it by x plus 1 and the 2, but you're going to change that sign in the middle. And why do we change that sign in the middle? Because really, look at those two things multiplied together. That's like the difference of squares now, right? Factored out. So I got to do it to the top and the bottom. And hopefully now what'll happen is the numerator will look a little better, and maybe it'll help us out with the denominator. So, and plugging in the limit of 3. So as I see this, a good thing to do now is go ahead and FOIL this. Now, again, it's the difference of squares, so I kind of know what the answer is going to be, but I'm going to FOIL it out just so you don't get too scared. Squared. Square root of x plus 1 times square root of x plus 1. Well, that's the square root of x plus 1 squared. They're going to cancel out. That's going to be x plus 1. Then I'm going to multiply this by 2 and get plus 2 roots of x plus 1. Right behind it, though, is minus 2 roots of x plus 1. And lo and behold, those two guys have canceled, which is what we wanted. And then a negative 2 times a 2 is minus 4. Now there is the entire top. And in fact, if you clean that up, that looks like x minus 3 on top. Now look at the bottom. Now I want to FOIL these two things together. Wait a tick. Look what we have on the bottom. We have these two things multiplied together, and one of them is an x minus 3. And I bet some of you are saying, holy cow, that is going to be really nice. Don't FOIL it. Leave it alone, right? Reason being, I don't know why I wrote it there. Reason being is it's going to come over here, right? And this guy's going to cancel this guy. Now be good. There's a 1 still on top, but this looks like x plus 1 plus 2. Now, what have we done? We multiplied by a fancy 1, right? This is just a fancy number 1 right here, right? It was nothing special, but it did clean up the top, and it ended up canceling with the bottom before I FOILed. So great, it made me less work. And I bet now if I evaluate that limit, so now I got to do the limit as x approaches 3, what do I get? I get 1 over square root of 4 plus 2, or 1 over 2 plus 2, 1/4. I found the limit. Now, what's cool about these things right here is if you guys wanted to, you could totally graph them and you would be able to see them, but I'm not going to take the time. So if you want, pause it, put it in Desmos, pause it, put it in your graphing calculator, and you should see that as you approach 3, you're not going to see much. You're just going to see what it looks like a normal graph, but there's a hole there, and that hole would be at 1/4 if you approach from either the left or the right side. All right, not really. Number 5. I was going to say last melon, but it's not. Let's go with this guy now. And I don't know what color you want. Let's do this pretty blue. Oh, maybe this one. The limit is 0. Plug it in. You get Oh my gosh, 1/4 minus 1/4 is 0 over 0. Oh, another time that this is bad. Direct substitution let us down. All right, that's okay. We know methods now, right? No square roots, so I'm not going to use a conjugate. No factors that I could cancel. So let's just try to clean this bad boy up. What do we want to do? Well, I think I want to get on the numerator. I don't like that it's two separate fractions, so I want to get a common denominator on those guys. So I'm going to give this guy an x plus 4, top and bottom. And I'm going to give this guy a 4, top and bottom. And at least then I'll be able to push those together like normal. So what does that turn into? That turns into the limit. I get pretty lazy and I should be careful. The limit of x to 0 of what? 4 over 4 times x plus 4 minus 1 x plus 4 over 4 x plus 4. And don't forget, all of that is still over x. All right, what does that turn into? Well, that turns into the limit as x goes to 0 of 4. Now distribute the negative through with it. So minus x minus 4 all over 4 over x plus 4 all over x. Hopefully now you've noticed that those 4's have canceled. And you now have the limit as x approaches 0 of negative x over 4 x plus 4 all over x. Still looks pretty gross. That's a complex fraction. We don't like that one bit. And so what do I have to do? I have to do copy dot flip, keep change flip, whatever you call it. So I have the limit as x approaches 0 of negative x over 4x minus 4 times, now it was divided by x over 1, so that's times 1 over x. Good news, kids. Look, the x's cancel there, and we are now talking about the limit as x goes to 0 of 1 over 4 x minus 4. And I think I can do direct substitution now. If I plug in 0, I get 4 times negative 4, which is negative 16, or negative 1/16. Again, grab a graphing calculator, look at it, and I really hope that the graph looks like when you're at x is 0, it should look like negative 1/16. That is you evaluating the limit, right? At x is 0. Whew! That was a ton, and wait, there's more. There's this thing called the squeeze theorem or the sandwich theorem or whatever the heck you want to call it, and that's going to take definitely another video. And so all I'm going to tell you to do is look at that theorem right there, 1.9, and it's got some very important things that we just have to memorize. The limit as you approach 0 of sine x over x is always 1, and the sandwich theorem shows that. The squeeze theorem shows that. And the limit of 1 minus cosine x over x, that's always 0. And again, we'll probably prove that in another video or in class or something like that. Have a great day. Stay happy, and I'll see you tomorrow.